Sorry guys, I cut myself off. My computer died. So I'll start the slide again. So when an electric pulse is applied to the transmitter, it generates an ultrasound pulse with the same duration. This ultrasound pulse propagates across the sample, and when it arrives at the receiver transducer, it generates an electric pulse. The ultrasound pulse propagates back and forth and creates additional electric pulses at the receiver, which is known as an echo train. The sound propagation time is determined by the sound velocity and hence by the associated elastic constant. The time evolution of the amplitude of the received pulse is defined by the sound attenuation. Both the ultrasound velocity and attenuation are intrinsic properties of the material and can be changed only by varying some external parameters such as temperature, magnetic field, or pressure. So here we have some examples of what it is that I was just talking about. So we have transmitted electric pulsars, so that's sent by the transmitter, whereas here we have our receiver. So we send these electric pulses into the material. It reflects back. So we haven't talked about reflection and refraction yet, but let's just assume that these signals are coming back. They are generating electric signals uh, and these are being received. So those are what you can see in the output signal here. So you can see these little red marks. Those are the received signals, and this is called our echo train. Of course, this is dependent on a couple of different properties. So it's dependent on the amount of material it passes through, so the distance that it travels into the body and then comes back, as well as the velocity. So how fast is that signal going, and then how fast does it come back? So the amplitude, of course, is the amplitude of the received electric pulses, or the amplitude of the waves that are coming back, are directly proportional to those different properties, so the distance as well as the speed, and that obviously has an effect on how much these signals are attenuated by. So we have our equation here of distance, which is equal to velocity times the change in time divided by 2. So that one you should be familiar with as an older equation. And then we have our object characteristics. So this is what I was just talking about. So the velocity and attenuation are intrinsic properties of each of the different materials within the body. So those are specific, again, to the material and don't necessarily change unless something external has changed. So this is how you would acquire all of these signals in a 2D nature. So if you have your object here, which is made up of two different materials, it seems. So this is material 1 and then material 2. So here we have our transducer and receiver, and so it's sending signals in and then receiving them back. So here it sends signals in and it reflects off this point, and it sends signals in and reflects off this point. And it continues to do this at every point in the x direction across this object. So we can see here what the resulting signals would look like. So we have, if we have our transducer at this point in time, we send a signal, the only thing that we're going to get is a reflection off of the bottom. So we end up with a signal that's quote unquote down here, but it's what the transducer receives back, or what the receiver gets, is a signal that is based on the distance that it traveled, the velocity at which it traveled, and then consequently the amount of time it took to come back. So here, if we move the transducer and it starts to come into contact with this object that's within our larger object, it's going to reflect back. So it's going to have an echo train here, right? So this particular signal that's coming back sooner, and usually at a much higher amplitude, then this signal is going to be closer to the receiver than this one will be. So if we continue that pattern and we continue to move this transducer along this whole object, we can generally get an idea of where this object is. And you can see that in the resulting graph down here, where this is, of course, scan time, and then this is our depth. So depth here is our velocity times time divided by 2. So because the particles along a sound wave do not move in synchrony, particles near to the origin of the sound wave begin vibrating before more distant particles. So sound velocity is the rate at which the vibratory energy is transmitted in a specified direction of propagation. Velocity is a vector quantity, which means that the direction as well as the magnitude must be specified. When the direction of propagation is not specified, the proper term is used as speed. So that's generally what we're looking at here, so velocity. Acoustic speed is greater in materials that are more rigid or less compressible. Acoustic speed in water and soft tissues is 5 times greater than that in air, and that in bone and metals is approximately 5 times greater yet. So you can see that reflected in this graph here, where it shows the velocity properties of each of the tissue types, where bone is significantly higher than fat, water, brain, all of the other soft tissues, which are generally around the same values as compared to air, which is quite small still. So here you can see just an example of the transducer as it's passing waves into the body. And then again, this is just demonstrating that our sound velocity is going to be lower for soft tissues than it is going to be for bone, and also demonstrating that we do send these pulses in at a specified time difference. So we know the time between each of the different pulses that we're sending in. So our sound velocity is going to be this equation here. So it's going to be the square root of 1 over Kp, which is going to be, K is going to be our compressibility, and P is going to be our density of each of these specific materials. So this is an example of a 2D cross-sectional image. This is going to be a B mode. A B mode is a two-dimensional ultrasound image display composed of bright dots representing the ultrasound echoes. The brightness of each dot is determined by the amplitude of the returned echo signal. So basically, we're doing the same thing that we just talked about. So we're scanning our transducer across the body. It's passing into the body, and it's receiving ultrasounds back. Again, we haven't talked about reflection or refraction yet, but it's receiving ultrasounds back at specified times and at different velocities, which basically tells us, and also, so of course, at different attenuated amplitudes. So all of this can tell us basically what material we've come into contact with and approximately where it is in terms of depth. So of course, if we sweep this across, this is sort of a CT scan-ish type procedure where we're sweeping this across the object and we're getting basically a slice of the object every single time. And what we end up with is our 2D image in the end. So here we have our B mode image frame rate. So basically, again, as we're talking about, we're sending these pulses in, we're receiving pulses in the form of an echo train, where here we have our original signal that's being sent in, and what we're receiving is signals that are being reflected back to the receiver. So here we have each of the different boundaries of this particular object, and then we have the final boundary of the entire object, and that's going to be at a diminished amplitude. So the time between these different pulses is going to be TR. So TR, which has to be greater than 2 times d, which is our maximum penetration depth, so that's going to be the entire length of the object, divided by the ultrasonic velocity, where our image frame rate is going to be 1 over TR times N, where TR is going to be our time frame between these two pulses, and N is going to be our scanning line or frame. So what's the frame number that we're talking about? Okay, so again, we're talking about attenuation of a signal based on the property that it comes into contact with, as well as the distance it has to travel and the time it takes to do so. So obviously these different attenuation properties are different for different materials in the body. So lung looks like it has the highest attenuation rate, followed by bone, and then air, muscle, and all of our soft tissues. But basically, attenuation is frequency dependent, so attenuation increases as frequency increases. And that is the end of part 1. So following this will be part 2 and then part 3.